Okay, we're starting. Moving on to chapter 3 today. Today we're going to start to learn some shortcuts to find derivatives. And so we'll finally start to get to do some really nice applications here. So we're going to talk about derivative properties and formulas. Technically in 3.1 we only learned about the exponential and the power rule, but I'll tell you some other things that will help us moving forward. Let's start out with properties. I'm talking about the algebraic properties of derivatives here. There are two important ones for us to know. So let's say C is a constant and F prime and G prime exist, right? Meaning they're differentiable, we can find derivatives, and then there are two properties that we can talk about derivatives. One is called the constant factor rule. This is basically a property of derivatives that says we can factor constants out when finding a derivative. So this says that the derivative of a constant times a function is actually a constant times the derivative. In other words, if we have a constant times a function, we want to find the derivative of that expression. We can sort of factor the constant out and find the derivative of the function, and that's the same. Why? We'll talk a little bit about that. Well, it just comes down to the limit definition, basically. Right? So if you have your y is equal to a constant times f of x, this would mean that your y prime would be the limit as h approaches 0 of c times f of x plus h minus c times f of x over h by the limit definition. Well, we know that we can factor constants outside of limits. And so this just becomes c times f prime. So you can factor constants outside of limits, therefore you can factor constants outside of derivatives. And that's called the constant factor rule. So an example here. By the way, throughout today, we can recall that we've done these guys before, so you can remember them. We know that the derivative of a constant is 0. We've also proven that the derivative of x is 1. We also showed that the derivative of x squared is 2x. We've also shown that the derivative of radical x is 1 over 2 radical x. We've also shown that the derivative 1 over x is minus 1 over x squared. So these are some things you'll know now. I'll teach you a general rule to derive these later, but we've actually proven these using the limit definition. So in my examples today, I reserve the right to call on any one of these rules that we know so far. And I'm going to call on one right now. So just to give you an example of the constant factor rule, let's say if y is equal to something like 5 radical x, and you want to find the derivative, notice that this is just 5 times a function. 5 is a constant, so that's like the c in the rule. What I can do is, to find the derivative, this is just going to be 5 times the derivative of radical x, according to that rule. And so that's just going to be 5 times, by that rule, that's 1 over 2 radical x. So this is 5 over 2 radical x will be the answer here. Right? So the idea is if there's a constant multiplying your function, you can just like leave the constant alone, differentiate the function, and that will be your answer. In practice, you don't really have to write this step. It's completely fine to me to jump from this step to that step. But in your mind, that's what you're thinking. Leave the constant alone, differentiate the function, and then multiply the answers at the end. Right? That's the constant factor. That's one important property of derivatives. Another important property of derivatives is the sum difference. This is a property that tells us how to differentiate a sum. So if I want to find the derivative of f of x plus or minus g of x, how can we do that? Well, it turns out to find the derivative of a sum, you just take the sum of the derivatives. Derivatives distribute across sums. So this is just going to be the derivative of the f of x plus or minus the derivative of the g of x. Right? So differentiate a sum of functions, you can just differentiate each individual term inside that sum. And again, why? It's based on the limit definition. Everything we know about derivatives will ultimately come from the limit definition. So if our y is equal to f of x plus g of x, let's just do it with a plus. Right? So that's our new function. This means that y prime would be the limit as h approaches 0 of this function evaluated at x plus h minus that original function all over h. But this is a fraction, I can split it in two. First I can rearrange the terms. So I can put the f of x plus h, expand the brackets, take this minus f and rearrange it over there, plus the g of x plus h. Expand the parentheses, put the g of x right here, all over h. I can split this sum into two parts. That's just that, plus that. Then I can divide. We have a rule that limits distribute across sums, so this gives me the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of g of x plus h minus g of x over h. This guy here is f prime, and this guy here is g. So it turns out to differentiate a sum of functions, you just take the individual derivatives and add them together. This is called the sum factor rule. So let's do an example of that. So example, let's say my function is something like x plus 1 over x plus 2 greater than x. Let's say I wanted to differentiate that. And again, I'll give you rules to deal with this before, but for now we can just assume we know these because we actually proved them. Then if you wanted to differentiate that expression, what ends up happening is you could think of this as differentiating each individual thing. That's how you would do it, right? And this is by the sum factor rule, sum difference rule. This part I can break down even further. There's a constant times a function. I can move that constant on the outside. And it's just that. And so now you do them one at a time. Derivative of x is 1 plus derivative of 1 over x is minus 1 over x squared, plus derivative of radical x is 1 over 2 radical x. That 2 just stays here. These can cancel. So I have 1 minus 1 over x squared plus 1 over radical x, and that would be your answer. So these are two important properties of derivatives that we can derive directly from the limit definition. If you have a constant times the function and you want to differentiate that, it's just the constant times the derivative of the function. If you have a sum of functions and you want to differentiate that, you just differentiate each part of the function individually. And again, writing down these steps, I'm really doing this for emphasis, but I don't actually care if you write that down. Don't have to write. So in a test, even though I say show your work, you don't really have to write that. Right? Because by the time the next test comes around, differentiating guys like these are going to be super easy. I'm going to assume you know all this. And it's okay to go directly from, oh, derivative of x is 1, derivative of this is that, derivative of this is that. You'd be able to do it a lot quicker without actually writing this out. I just want to emphasize, if you have a sum of things and you want to differentiate that, just take the derivative of each individual thing. Right? And sum in the general sense. So if there were subtractions, you just, I didn't do one of the subtractions. But if there were subtractions, you can also do each individual. So those are two important properties. Any questions on that? So those are the properties. And that's going to facilitate us learning some new formulas. So what I want to do is so I'm not going to justify these two things I'm going to tell you. I'm just going to tell you them. We're going to take them as fact and we're going to move on. The first one I actually proved from scratch in my 1207 class, but I don't think there's going to be much insight to that for this class, for what we're doing. So I'm just going to tell you the derivative of the function e to the x is, does anyone know? Derivative of e to the x. Yeah?
E to the x.
It's e to the x. Literally, this is the only function besides 0 whose derivative is itself. Right? That's why it was a very important function. When I was talking about the exponential function, I said, oh, this is important for calculus. This is one of the reasons why it's very nice to deal with in calculus, because if you're doing like a derivatives and integrals, you essentially don't have to do anything. It gives you its own slope at any given point. So this is a rule that, again, it can be proven, but I don't want to do it. If you're interested in that, you can watch my video for my 1207 class. And where I actually prove that. But we'll take that without proof. The derivative of the exponential function, e to the x, is itself e to the x. Okay. This also means, by the way, if you want to differentiate a constant times e to the x, well, that's just going to be a constant times the derivative of e to the x. And that's going to be just the constant times e to the x. So multiplying by a constant doesn't change anything. So derivative of constant times e to the x is, again, the constant times e to the x. So e to the x is very nice in that regard. Okay? So that's one rule we'll take without proof. We're going to actually use this fact to prove other things. The next thing we'll take without proof is a very important derivative rule. It's one of the fundamental ones. It's called the chain rule. Now, even in my 1207 class, I didn't prove this one because it is kind of hairy. You need to understand limits beyond the extent that the typical Calc 1 or Calc 2 student would understand limits in order to prove this, so I'm just going to tell you what the answer is. This is a rule that tells us how to differentiate composite functions. So if you have something that looks like f of g of x, and you want to find the derivative of such a function, who here knows the chain rule? I know a few of you have done calc before. Yeah, how you differentiate it?
F prime of g of x times g prime of x.
F prime of g of x times g prime of x. So again, you can prove this from the limit definition, but you have to actually be careful with how you're using the limits. But this is a rule, a very fundamental rule. It's called a chain rule. Basically, it deals with differentiating composite functions. So if you have a function, you have an inside function that you plugged inside of it, and you want to differentiate that thing, you differentiate the bigger function, the surrounding function, and then you multiply by the derivative of the inside. So it's the derivative of the outside times the derivative of the inside. That's basically how you do the chain. So let me do an example here. Let's say your function was something like this. The square root of x squared plus 1. Now, we haven't derived that, so we don't actually know the answer to this yet. But you'll notice that it is comprised of a bunch of functions that we do know about. The radical, we know how to differentiate a radical x. X squared, we know how to differentiate. And the 1, we know how to differentiate from this. But now it's kind of weird because we're mashing several of these functions together. And one way you can think about this is to think of it in terms of two functions. There's an outside function and an inside. Yeah.
So, like, how do we determine what's outside function and what's inside function?
That's what I'm going to talk about now. So here's how you could think about this. So let's sort of determine what would you guess would be the outside function? What would you guess?
The radical x squared.
The radical, right? Because here's the radical is covering like literally the whole thing is expanded by the radical, right? And you have something inside the radical, right? It's not just a radical x. It's a radical of some things that is other than x, right? So you sort of think of this guy as your inside function. So I'd kind of let my g of x be like this guy. The f of x would be just the radical function. And then you can test your theory, right? If these, so pretend we're not here, think back to our material on test 1. If I gave you these two functions and asked you to find f of g of x, what would the answer have been? It would be this answer, right? So this guy is a composite function. You can think of it as f of g of x, where there's an inside and an outside guy. So let's actually look how we want to differentiate this guy. I know I'm just talking to you a lot, but the main point of today's class is to introduce the rules to you, not so much the examples. I want to illustrate a little bit while I'm going on. But we'll slow down with examples later. We'll actually do the chain rule again in 3.4. So, but I really want to do this rule because it will help me facilitate me teaching you other rules. So here I have this guy, and inside it I have this guy. So the rule says we want to differentiate the outside function, leaving the inside alone, and then multiply by the derivative of the inside. So how would we do that? So if we have a radical of something, what should the derivative look like? Yeah.
So if we have it should be by parenthesis x squared plus 1 parenthesis to the 1/2, then we find the derivative of that function and multiply the inside derivative of x squared plus 1.
Well, we don't have to do the half yet. Don't worry about the half yet. We have a rule directly with a radical here, right here. So if we want to differentiate the radical of something, what do? We put 1 over 2 times the radical of the thing. So we start there. Put 1 over 2 times the radical of the thing. Right? This thing that I just wrote down is this part of the rule. I differentiate the outside function. I pretended this guy was just x, applied a rule to the outside, and that would be what I get. But because that's not just x, there's an inside function here, I have to now multiply by the derivative of the inside function. So I'm going to multiply by the derivative of this. How do we differentiate this, x squared plus 1? Do one at a time. It's the sum rule that we're applying here. So you differentiate the x squared, then you differentiate the 1. Derivative of x squared is 2x plus derivative of 1, 0, because it's a constant. And so this derivative, I can take this 2x and multiply it on top. Those guys would cancel. And so I have x over the radical of x squared plus 1. So this is an example of me applying the chain. Here's another example of me applying the chain. Suppose I'm calling function g of x u, right? So u is like g of x. How would I differentiate e to the u? Meaning there's an e with something plugged inside of it. According to the chain rule, what would happen? Yeah. Well, in this order, we first take the derivative of the outside function. Right, so that's e to the u, because the derivative of this guy is itself. But because there's an inside function, I now have to multiply by the derivative of the inside function, according to the chain. So in other words, usually they write it in the other order, that's u prime e to the u. So if you want to differentiate e to any power, the derivative of that function is the derivative of the power times the original function. This is another important rule. You have to have it memorized. So let's actually do one example there. So let's look at how would I differentiate e to the x squared. Yeah.
Would it be 2x e to the x?
So we're going to put the derivative of its power, right? So the power here is x squared. You know how to differentiate x squared. So it's the derivative of the power, which is 2x times, as he said, e to the x squared. Take the derivative of the power times the original function. That is the derivative of e to any function. Okay, so here's another example. It's going to give us a rule. We're going to derive the derivative of ln. Does anyone know what the answer is? Yeah?
1 over x.
It's 1 over x. Let's actually prove that. The derivative of ln x is 1 over x. So here's the thing. I'm going to set a function equal to ln x, and I'm going to find its derivative. Set g of x equal to ln x. Now at the moment, I don't know anything about ln x in terms of what its derivative is, but I do know about the exponential. How can I introduce an exponential into this? because I don't know anything about the ln, I want to get rid of the ln. How do we get rid of an ln to solve an equation? Yeah?
You raise it to an e.
Raise both sides to the e. So what I'm going to do is I'm going to take e to that and e to that. That's how we deal with exponential log equations if we want to get rid of a log. Because I don't know anything about ln, so I want to get rid of it. So I do that. And so what I have now is e to the g of x equals, what's e to the ln x? It's just x. And now what I'm going to do is I'm going to differentiate both sides of this equation. If this is equal to that, then the slope of this is equal to the slope of that. So let's differentiate both sides. What's the derivative of e to the g of x? E raised to the function g of x. Yeah? G of x times e? No. Yeah?
Derivative of g of x times e of g of x.
Right. To differentiate e to any power is the derivative of the power times the original function. So I'm going to take the derivative of this, which is g prime, times the original function, e to the g of x, equals, what's the derivative of x? 1. Now, my function was g of x equals ln x. I want to figure out the derivative of ln x. So what I'm really after is g prime. So let's just solve this equation for g prime. E to anything is never going to be 0, so I can divide by it. So that's 1 over e to the g of x. Well, what was e to the g of x? That was just x. So this is actually just 1 over x. So if my function is ln x, its derivative is 1 over x. This gives us a rule. The derivative of ln x is 1 over x. Yeah, all these rules that I'm putting asterisks on is because I expect you to memorize them. Like right this second. No, not by the next class. We're just, I told you guys that this class is moving sort of fast because I'm giving you a lot of rules right now because we're going to be using them pretty soon. Yeah.
Are we going to have to know how to do the proofs?
No. I'm not going to ask you to prove any of the rules, right? I want you guys to appreciate that these rules don't come out of nowhere. There's a reason for everything. And so I'll show you some proofs, but no. I don't expect you to know how to do this. At least not yet. We'll be doing similar type problems, but you should know this. You should know the derivative of ln x is 1 over x. You should know the derivative of e to the x is e to the x. You should also know the derivative of e to literally anything is the derivative of the thing times the original function. So that I expect you to derive it, not necessarily. No. I'm never going to ask you to prove a derivative. So we have that. Now, by the chain rule, and you can literally use the chain rule to generalize any other rule. That's why it's a very fundamental derivative rule. Let's say I don't have ln x, I have ln of some function, right? How do I deal with that? What is the derivative of ln of u, where u can represent any function? Well, according to the chain rule, that is going to be the derivative of the outside. We know that the derivative of ln of x is 1 over x, so that's going to be 1 over u. But then we have to multiply by whatever the derivative of whatever that inside function was, which is u prime. So that's me applying the chain rule. So this gives us another important rule. The derivative of ln of anything is the derivative of the thing over the thing itself. By the way, if you hate memorizing things and you want to memorize as little as possible, and you can actually memorize like half the formulas I give you today. It's much better to memorize the chain rule version of a rule than the basic version of a rule, because this is far more general. This literally will work with only x, whereas this will work with anything, right? And so, in fact, this rule kind of implies that rule, right? If I take x to be my u, its derivative is just going to be 1, right? So by memorizing this rule, I'll automatically memorize that rule. So if you have to memorize one of them, it's the chain rule version that you have to memorize. But really the truth is, this is going to show up so often, you're going to end up memorizing it anyway, just by doing your homework and doing quizzes and stuff. But yeah, I expect you to memorize this. Now let's look at the main rule of this chapter. In 3.1, there was one big rule that was geared towards teaching you, and that's the power rule for derivatives. So let's actually look at the power rule. And I can kind of erase this now, because the power rule is actually going to take care of all of these rules that I have up here. In fact, we can probably use the power rule and reprove all of these things here. So here's our goal. We want to find the derivative of something that looks like x to a power. So something like x to the 1, x to the half, x to the 3 over 2, x to the 15, x to any number. I want to be able to differentiate that expression. And using this expression, in fact, I can differentiate any polynomial, because a polynomial is just a sum of powers of x's, right? And so those are very important functions. Now I'm going to know how to differentiate by learning this rule. So let's actually figure that out. So set g of x equals x to the n. My goal is to find g prime. Here's how I'm going to do it. I don't really know how to deal with the powers, but I remembered that one of the uses of logarithms is to get rid of powers. Logs turn powers into products, so let's actually do that. What I'm going to do is I'm going to take the ln of both sides. Now there's a rule that says I can take this power and I can bring it down in front. Now let's differentiate both sides. Here's ln of something. How do I differentiate ln of something? I take the derivative of the thing and put it over itself. So the derivative of this side is going to be g prime divided by g equals. How do I differentiate this? Well, n is just a constant. N is a number. So the constant factor rule says to differentiate this, I leave the constant alone and differentiate the function. What's the derivative of ln? Well, it's 1 over x. Now, let's solve for g prime. So this means my g prime of x is going to be n over x times, multiply both sides by g of x. Well, what was g of x? What was g of x? It's x to the n. G of x was x to the n. So this is equal to n over x times x to the n. What is that? That's really n times x to the n over x. Laws of exponents now applies. This is x to the 1. To divide two things at the same base, you subtract the powers. So this just becomes n x to the n minus 1 is your g prime. Hence, we now know the power rule. We can differentiate x to any constant power. i.e., the derivative of x to the nth power is nx to the n minus 1. Very important derivative rule. In fact, it has a name, this rule. It's called the power rule. Four derivatives for emphasis, because integration, antiderivatives also has a power rule. But this is the power rule for derivatives. It is the rule that tells us how to differentiate x to the n. One thing I want you to note here, and it's actually super important, n is a constant. So this really tells me how to differentiate x to any constant power. If the power is not a constant, this rule does not apply. Let's apply the power rule a few times. Let's rederive all those rules that we painstakingly derived using the limit definition. So things like differentiating a constant, differentiating x, differentiating radical x, differentiating 1 over x. Let's do all of that. And you kind of already know what the answer should be, so that should be no problem. Just do an example. Let's differentiate a constant. How can we differentiate a constant? No. This is actually equal to the constant times x to the 0, right? Because x to the 0 is 1 by our exponential rules. This means I can leave the constant alone and differentiate x to the 0. But according to this rule, what would happen? The power is going to come down and multiply everything. That's going to give me c times 0, x to the minus 1. Well, that's just all 0. So the derivative of a constant is 0, according to the power rule. What about the derivative of x? Well, this is just x to the 1. So the derivative, according to the power rule, I'm going to take that 1, bring it down, subtract 1 from the power. So this is just 1 times x to the 0, but that is also 1. So that is 1. So the derivative of x is 1. Power rule makes it kind of easy, right? You remember when we had to do a limit definition for that? What about for x squared? Well, in this case here, n is just 2. So according to the power rule, I can take that 2, bring it down, and then subtract 1 from the power. So that gives me 2x to the 1, which is just 2x. So the derivative of x squared is just 2x. Let's look at radical x. The trick here is to rewrite that as x to a power. We know that from our exponential rules. I can write it as that. And now a half is like my n in the power rule. So what I would do is I bring the half down and then subtract 1 from the power. A half minus 1 is minus a half. And so this is 1 over 2 times 1 over x to the half. Or you can think of that as 1 over 2 radical x. By the way, from now on in general, it's completely fine to leave your answer in this form. You don't have to do all that. This is fine for the answer. I went further because I want to show you that it's exactly the same as what we had before. What about 1 over x? Again, I would write that as x to a power. This would just be x to the minus 1. Then I apply the power rule. Minus 1 comes down. Subtract 1 from the power. Minus 1 is minus 2. So I get minus 1 over x squared. So you realize the power rule is actually very powerful. It can help us deal with a lot of, pretty much x to any power, I now know how to differentiate. X to any constant power. We'll end with one more example. I'll have you guys help me with this one since it's not one that we've seen yet. My y is 3x to the 4th minus 7x plus 2 over x cubed. Find y prime. How do we do this?
You can use the one rule that is like the derivative of each part.
Sure, yeah. So here I have a bunch of functions separated by pluses and minuses. So I'm going to use the sum difference rule. Just differentiate each part. Okay, so we know that we want to differentiate each part. Now what?
The first part is 3 times the derivative of x to the 4th.
Right, so the 3 is just going to stay because that's the constant factor rule. And what's the derivative of x to the 4th? 4x cubed. Right, so that's the derivative of this. Now move on to the next guy. What's the derivative of 7x? Well, it's 7 times the derivative of x. Derivative of x is 1. You can get that from the power rule. So it's 7 times 1. Or just 7. In fact, that you can sort of think of as a rule from now on. The derivative of a constant times x is just a constant. Right? You can think of that, it's just the slope of that line. Plus, now I differentiate that back. How do you differentiate that back? 2 over x cubed.
Bring the x, bring the x cubed up.
Right, we can use the laws of exponents to actually rewrite that. Realize that this is 2x to the minus 3. And now we have a rule to deal with that. So what do? The 2 stays. How do I differentiate x to the minus 3? Bring the power down, subtract 1 from the power. So that's 3x to the minus 4. So in other words, let me rewrite this. This would be 12x cubed minus 7 minus 6x to the minus 4. And that would be my derivative. Which you can see without the limit, you can imagine with the limit definition, that would have been crazy, right? X plus h raised to the 4th power, to expand that would have taken you forever. Then doing with 1 over x cubed, x plus h cubed, that would have taken forever. But with the power rule, it's pretty easy. So, but I want you to appreciate the easiness of getting to that answer. Also appreciate that our old concepts of derivatives still apply. So this function gives me the slope of that function. This function gives me the rate of change of that function. If this function was a position, that would give me its velocity. All that stuff that I said about derivatives before still applies. But we'll do some more examples and learn some more rules next time. We'll stop there.